Hi class! So today, here in Advanced Engineering Mathematics for Civil Engineers, we are now going to discuss the third part of Laplace Transform. So for this topic, students must be able to discuss and apply the properties and theorems of Laplace Transform. So that is Laplace Transform of non-integer powers of t and Laplace Transform of integrals. So we will start our discussion now. Okay, so for our next topic, we are going to use the concept of gamma function. So we are going to discuss first about gamma functions. Okay, so we will discuss gamma functions for positive integers. So gamma functions, it is actually an extension of factorial. Okay, so we are going to use to find the transforms of non-integer powers of t. We will use gamma functions for that. Okay, so gamma functions, it is denoted by this symbol. So this symbol means gamma of n. Okay, so gamma of n, okay, this is actually equal to n minus 1 factorial. So this is the relationship between gamma and factorial. So as we know, factorial, let's say factorial of 5. Okay, we know that the factorial of 5 is just equal to 5 times 4 times 3 times 2 times 1. You can actually um, compute that in your calculator, right? A factorial of any number. So, okay, so this is the relationship between gamma n and factorial. So again, gamma of n, that is equal to n minus 1 factorial. So from this relationship, okay, we can actually say that n factorial is equal to gamma of n plus 1. So we just, we just interchanged it. Okay, here, if gamma n is equal to n minus 1 factorial, meaning to say, let's say for gamma of 5, we know that the gamma of 5, if we use this relationship, okay, gamma of 5 is equal to 5 minus 1 factorial. So that will be 4 factorial. So 4 factorial will just be 4 times 3 times 2 times 1. So what happened there is that we did not include 5 here, okay, for gamma. Okay, so okay, now if the function here is n factorial, okay, meaning to say if we resolve it into its equivalent gamma function, so that will be gamma of n plus 1. Okay, so from this relationship, we can also say that gamma of n plus 1 is equal to n, okay, times gamma of n. So here, as we know, gamma of n is equal to n minus 1 factorial. Okay, so that will be n minus 1 factorial. And we know that in n minus 1 factorial, we did not include the n itself in the factorial. Let's say the n nga is 5. Okay, so if it's gamma of n, okay, that will just be 4 factorial. Or gamma of 5, that will just be 4 factorial. So here, if the question is n factorial, let's say 5 factorial, okay, so the gamma of n, okay, that is 4 factorial. So we need to multiply n here to make it 5 factorial, right? So n times gamma of n, that is equivalent to n factorial, meaning to say this n, okay, n times gamma of n, this is also equivalent to gamma of n plus 1. Okay, so you get it. Okay, so from here, now also, we will use this, this formula in order to solve for gamma, okay, of any positive integer. Integer meaning to say that's a whole number, ha? Okay, so the gamma of n, okay, that is actually equal to the integral of e raised to negative t times t raised to n minus 1 times dt from 0 to infinity, wherein the n here is the given n here, ha? Okay, so we can also use this, that the gamma of n plus 1 is equal to integral of e raised to negative t times t raised to n dt, okay, from 0 to infinity. So we are going to use this, this formula in order to solve for gamma n, okay, for positive integers. Now, for gamma of negative integers, okay, that is actually infinity. The gamma of any negative whole number, that is infinity. Okay, so the reason for that is if we apply negative n here, okay, if we use negative integer here and we substitute it here, so that will be negative minus 1. So that will be negative factorial. And just so you know, there is no negative factorial, right? So if you try to solve that in your calculator, no, I can't find my calculator. Where is my calculator? It's not here. Where is my calculator? And anyway, so if you try to input that in your calculator, negative whole number and its factorial, it will be math error. So because that is infinity. Okay. So let's try solving problems for gamma function. So we have here gamma of 1. So we are going to solve this. Okay, we are going to solve the gamma of 1. So for the solution, okay, we are going to use our formula here that the gamma of n is equal to integral of e raised to negative t times t raised to raised to n minus 1 rather, time dt from 0 to infinity. So we will just substitute 1 to n here, no, and also here. So this will be n. We will substitute 1 here. So this will become 1 minus 1. Okay, so that will just be 0, right? 0, t raised to 0. And we know that t raised to 0, that is actually equal to 1. Right, equal to 1. T raised to 0 is 1. So any number raised to 0, that will just be 1. So if you multiply 1 by e raised to negative t, so that will just become e raised to negative t, no? dt from 0 to infinity. So we will integrate this, and we know that the integral of e raised to negative t dt will just be as it is, no? But we will have a neutralizing factor. Okay, so we need the reciprocal of the coefficient of variable t here. So that is negative 1. So negative 1 over 1, that will be the reciprocal. So we just multiply that here. So this will become negative 1, which we did not include that na dito. So this will become e raised to negative times e, or negative e raised to negative t. So we will evaluate this from 0 to infinity. Okay, so substituting the upper and lower limit, so that will just be, we factor out negative here. So this will become e raised to negative infinity minus e raised to 0. And we know that e raised to negative infinity, that is just 0. And e raised to 0, that is actually 1. So negative 1 times negative, so that will become positive 1. So the gamma of 1 is actually 1. Okay, so we can try to check this, no, using our formula. Okay, so for gamma of n, okay, or gamma of 1, that will just be 1 minus 1. So that will be 0 factorial. And if you try to input that in your calculator, 0 factorial is actually 1. Okay, so this answer is correct. Now, let's proceed to number 2. This is gamma of 2. Okay, so for our solution, okay, so we are going to use our formula here. So our formula is gamma of n. Again, so we will just substitute 2 for n. No? So this will be gamma of 2. Okay, and the n here, we will substitute 2. Okay, so this will become e raised to negative t times 2. 2 minus 1 is 1. So this will just become e raised to negative t times t. So we will integrate this. So to integrate this, now we are going to use integration by parts. So this is a combination of exponential function and algebraic function. So we will use IBP. Okay, so using IBP, we will assign a function for u and a function for dv. Okay, so for u, we will place here the function that comes first in Liate. So algebraic comes first before exponential. So we will put our algebraic function here. So u is equal to t, and we will place the remaining function here at dv, including dt. So dv will be equal to e raised to negative t times dt. So we are going to derive or solve for the derivative of u is equal to t, and that is just du is equal to dt. And for dv is equal to e raised to negative t dt, we will just integrate it both sides. So integrating this, okay, so the here, and d will just be cancelled. So this will become v is equal to, and the integral of this is just negative e raised to negative t. So from here, we will use IBP, that is uv minus integral of v du. So our u here is t, and our v here is negative e raised to negative t. That's why this becomes like this, no? Okay, so we will evaluate that from 0 to infinity minus integral of v du. So our v here is negative e raised to negative t, and then our du is dt. So we will just put that here. So this is from 0 to infinity. So simplifying this, okay, so this will become positive, no? Positive integral of e raised to negative t dt. So, the integral of that will just be negative e raised to negative t. Okay, we will evaluate that from 0 to infinity. Okay, so we can now no, evaluate this. So, for the first function here, or term here, okay, we will just substitute the upper and lower limit. So, we factor out negative here, so this will become infinity times e raised to negative infinity minus 0 times e raised to 0. And we know that, okay, so later we will simplify this. Okay, so we will proceed first here. So we factor out the negative here. So we substitute the upper and lower limit to variable t. So this will become e raised to negative infinity minus e raised to 0. Okay, so from here, we are going to evaluate this. Okay, so as we know, e raised to e raised to negative number, that is actually 0. And since this will be multiplied by 0, so this will become 0. And then e raised to negative infinity, that is, no, that is 0. And then we have here e raised to 0. And we know that e raised to 0 is actually 1. So this will become negative 1 times negative, so that will be positive 1. So this will now be the gamma of 2. So that is actually equal to 1. So we can also check this using our formula, gamma of 2. That will be 2 minus 1 factorial. And we know that 2 minus 1 is 1. So 1 factorial, that is actually 1. No? So gamma of 1 factorial is actually equal to 1. So gamma of 2 here is 1. So we have the correct answer for this. Number 3, so this is gamma of 3. So for our solution, again, we are going to use our formula here. We just substitute 3 to n. Okay, so we substitute 3 here for this n and for this n. So gamma of 3 is equal to integral of e raised to negative t times t raised to 3 minus 1 dt from 0 to infinity. And 3 minus t, that will just be 2. So this will become t squared. Okay, so integrating this, again, we are going to use integration by parts here since this is a combination of exponential and algebraic functions. So using IBP, we will assign functions for u and functions for dv. So for u, we will assign here what comes first in the given, no? So in Liate. So the function that comes first in Liate here is algebraic. So we will put the algebraic function here at u, and the remaining function we will put here at dv, including the dt. Okay, so this will be dv e raised to negative t dt. So we will derive u is equal to t squared. So solving for its derivative, this will become du is equal to 2t dt. Okay, and solving for the integral of the both sides of dv and this side, no? So we will integrate this. So the integral sign and d here will just be cancelled. So we can solve for v. So the integral of e raised to negative dt, as we know, that is just negative e raised to negative t. Okay, so from here we will apply integration by parts, uv minus v du, or integral of v du minus integral of v du. So our uv, so u is t squared, and then v is negative e raised to negative t. So this will be that term, minus integral of v du. Our v here is negative e raised to negative t. Okay, and our du is 2t dt. So we will simplify this. Okay, so if we simplify this one and this one, so this will become positive, right? Okay, so we can also factor out 2 here. Okay, and what will remain here is t. So e raised to negative t times t. Okay, so we will integrate this further. Okay, this term. Okay, so we will use by IBP again for this, since this is a combination of exponential and algebraic function. No? So again, using IBP, we will assign functions for u and dv. For u, we will put the algebraic because that comes first in Liate, no, before exponential. So we will put t here, and here in dv we will put the remaining function, which is e raised to negative t, together with dt. Okay, so we will derive u is equal to t, so that will become du is equal to dt. Now we will integrate this both sides. Okay, so we can solve for v here. So v is equal to negative e raised to negative t. So again, using IBP here. So don't forget to include this, ha. Okay, baka makalimutan mo. Don't forget this. Okay, so don't forget that. So we include that here, and then we apply IBP again. UV, so our U here is T, and then our UV, our V is this. Okay, so don't forget also that we factor out 2 here, ha? Okay, so we just include that here. So UV, that is T, and negative e raised to negative T, so this will be their product, minus integral of V du. Our V is this, okay, and our du is this, so this will be that, that term, okay. So, from here, okay, we can actually integrate this directly. We can integrate this. This is just integral of e raised to negative t dt. So, it will become positive here, ha? Okay, since negative times negative. So, we can integrate this. So, integrating this will actually become negative e raised to negative t, right? From 0 to infinity. So we just we just distribute 2 here. So 2, it will be distributed here, and it will be distributed here. That's why it's multiplied by 2 here. Okay, so from here we can now evaluate this. So evaluating the first term, so we will just substitute the upper and lower limit. So we factor out negative, so this will become infinity squared times e raised to negative infinity minus 0 squared times e raised to 0 minus, okay, we factor out this minus or negative sign. So that will be 2 times infinity times e raised to negative infinity minus 2 times 0 e raised to 0. Okay, also we factor out this negative here, so we factor out. Okay, this will become 2 e raised to negative infinity minus 2 e raised to 0. So evaluating this, we know that e raised to negative infinity, that will just be 0. And then this will just become 0 since it is multiplied by 0. So also for this, the e raised to negative infinity, this will just become 0. This will also become 0. This will also become 0 to e raised to negative infinity, no? And then we have here e raised to 0, so that will just be 1. So this will be negative 2 times 1, so that will be negative 2 times negative here, so that will become positive. So the gamma of 3 is actually 2. So we can check this, no, using our formula. So for gamma of 3, that will just be 3 minus 1. That will be 2 factorial. And we know that 2 factorial is just 2 times 1. Okay, so 2 factorial is just equal to 2. Okay, so we have the right answer for this. Okay, so let's proceed now to number 4. So this is gamma of negative 1. So for gamma of negative 1, okay, as we know, this will just yield to to infinity. This will give us an infinite answer. Okay, so we will apply our formula here, okay, in order for us to prove that this will just yield to infinity. Okay, so we will just substitute negative 1 to n. Okay, so this will become negative 1 minus 1, t raised to negative 1 minus 1. Okay, so simplifying this, this will become integral of e raised to negative t times t raised to negative 2 dt from 0 to infinity. So here, no, we will try to use IBP here. So using IBP, we will put the function here at u, no, the algebraic function we will put here at u, and for dv we will put the remaining function, which is e raised to negative t, including dt. Okay, so we will derive u is equal to t raised to negative 2, so that will become du is equal to, so we apply power rule here, so this will become negative 2 times t raised to negative 2 minus 1, which is raised to negative 3, no, dt. Okay, so here naman, we will integrate this. So integrating this, okay, we can solve for v. So this will just become negative e raised to negative t. Okay, so applying IBP uv minus integral of v du. Okay, so this will just be uv. So this is our u. And then this is our v. So this will be that. Okay. And then minus integral of v du. So our v is this, negative e raised to negative t. And our du is this. So we'll just multiply it here. So simplifying this, okay, so simplifying this, as we can see here, no, this will become negative times negative times negative, so this will be negative 2, so we just factor out 2, and this will be integral of e raised to negative t, t raised to negative 3 dt from 0 to infinity. So as you can see here, okay, from our first solution that we did here, okay, so this is from negative 2, okay, and as we can see here, the result is raised to negative 3. Okay, so as you can see here, if you try to apply integration by parts again, so this will just yield t raised to negative 4. And then if we apply IBP again for that, that will become t raised to negative 5, t raised to negative 6, and so on and so forth. Okay, it will go on and on. It will continue on. Okay, that's why for this, no, for gamma of negative integers, that will just yield to infinity. Okay, so this is infinite. Okay, so now we will now proceed to the gamma functions for non-integers. So the non-integers that we're going to talk about here are just fractions with denominator 2. So basically, this will just be 1 half, 3 halves, 5 halves, 5 halves, 7 halves. So we talked about earlier in the gamma functions for positive integers, no? That is just for positive integers, right? So also if you try to input in your calculator, let's say 1/2 of 1/2 factorial, let's say 1/2 factorial. Okay, as you can see, okay, this will not give us an answer. So this is math error, but actually there's a an equivalent for that 1/2 factorial. Okay, there's a value for that, so we will talk about that here. Okay, so as we know, okay, so for this, no, we are going to use this this established equivalent. Okay, that the gamma of 1/2. Okay, the gamma of 1/2 is actually, if we apply factorial, so the gamma of 1/2 is just 1/2 minus 1 factorial, and that is actually negative 1/2 factorial, right? And this is already established, okay, that gamma of 1/2 or negative 1/2 factorial, this is actually equal to square root of pi. Okay, so we will no longer we will no longer derive, okay, why this is the equivalent value for this, no? So this is already an established value, so we will not derive this anymore. Okay, just remember that negative 1/2 factorial or gamma of 1/2, that is actually equal to square root of pi. So we will use this here. Okay, so for positive non-integer with denominator 2, so let's say 1/2, 3 halves, 5 halves. Okay, so we will try to solve them. Okay, their factorial. So let's say 1/2 factorial, 3 halves factorial. So we are going to use that, okay, in solving for Laplace transform, because we know that in Laplace transform, okay, let's say for Laplace transform of t raised to n, the formula there for t raised to n, okay, for the Laplace transform for that, okay, that is actually equal to n factorial over s raised to n plus 1, right? So we are going to we are going to apply factorial there. Okay, what if the exponent of t is not an integer? Okay, it's not a whole number. Let's say that is 1/2, t raised to 1/2. How are you going to solve for 1/2 factorial, right? So we are going to talk about that here. Okay, so this is just limited nga lang for fractions with denominator 2. Okay, so for n factorial, okay, so let's say the n here is fractions with denominator of 2. Okay, so that n factorial, we know already this, no, this relationship that n factorial is equal to gamma of n plus 1, and this is also equal to n times gamma of n. So if we are going to solve for this, no, so gamma of n, this will also be equal. Okay, so from here, okay, so gamma of n, this is actually equal to gamma, okay, of n minus 1 plus 1. Okay, so we know this, that if we simplify this, negative 1 plus 1, that will just be 0. So basically, it's just gamma of n. Okay, but from here, we are going to apply something here, that the gamma of n minus 1 plus 1. So this will serve. Okay, so we will parallel this here. Okay, so this n minus 1 will represent this n. Okay, and this plus 1 will represent this plus 1. So meaning to say, we can rewrite this gamma of n minus 1 plus 1, we can rewrite it this way. So again, we will treat this as n. So this will be the equivalent for that. Okay, n plus 1 plus 1. Okay, so we will apply this. Okay, so here, if we are going to apply this, so this n minus 1, okay, we will just put that here outside the symbol, no, and then gamma of n minus 1. Okay, so we just applied this, okay, so we will apply that in our solution for this. Okay, also for for negative non-integer, so meaning to say this is, let's say, negative 1 half, negative 3 halves, negative 5 halves. So we will use this relationship. Okay, so for negative n factorial, that is actually equal to gamma of negative n plus 1. So we already know this already, this relationship. So this is actually from here, just also, no? Okay, so we just see instead of positive n here, so this is negative n. So if this is positive here, it will be negative n here. Okay, so from here, no, we will apply this. So this is the formula for this, no. So we are going to apply this, no, that we can rewrite this gamma of negative n plus 1. We can rewrite it this way, right? So we can rewrite it this way. So this is negative n plus 1 plus 1. Okay, but since we added plus 1 here, okay, our rule, if we add plus 1 here, we have to multiply this by 1 over negative n plus 1. We will just multiply this by the reciprocal of this. Okay, so the reciprocal of negative n plus 1 is 1 over negative n plus 1. So that will be our rule here. Okay, so we will see the use of this, why we added 1 here, no? And then, again, okay, so if we add 1 here, we have to multiply this by 1 over negative n plus 1, so that this function will not, be changed. Okay, so we will apply this, no, these concepts in solving for factorials of non-integers or specifically fractions with denominator 2 for this. Okay, so let's start. Okay, so for number 1, this is 7 halves factorial. Okay, so to solve for 7 halves factorial, okay, if you use calculator for that, as you can see, it will not give you an answer. That is math error. Okay, so for 7 halves factorial, we are going to apply this. Okay, so this is no, this is a positive non-integer with denominator 2. Okay, so we will apply this. Okay, so applying this. Okay, so for our solution, so we will rewrite this. Okay, so this 7 halves factorial, okay, so this will be that n factorial. Okay, if we rewrite it this way, okay, so this will be gamma of n plus 1. So this will become gamma of 7 over 2 plus 1. Okay, so after this, no, after we rewrite it this way, we can rewrite it further this way. Okay, so this will also be equivalent. Our n here is 7 halves. Okay, so we will rewrite it this way. So this will become 7 halves gamma of 7 halves. Okay, so this will be equivalent to this, no? So this is also equivalent to this. Okay, so after that, okay, so we can rewrite now. Okay, we can rewrite this gamma n. So this is gamma n, right? So this is gamma n. We will rewrite it this way. Okay, we will rewrite it this way. So we will rewrite gamma of 7 halves here. Of course, we have to include this also, so that will be 7 halves. But we will rewrite 7 halves as n minus 1 plus 1. So n minus 1, that is 7 halves minus 1. So that is 5 halves. So 5 halves plus 1. Okay, so this is just also equivalent to this, no? But what we're going to do here, okay, so we are going to rewrite it. No, we are going to rewrite it this way. Okay, so this is also equivalent to this. Okay, so this will become, our n minus 1 here is actually 5 halves, ha? Okay, so this will become 7 halves, and then we apply this, no? We can factor out n minus 1 here, so we can factor out 5 halves here, so we factor that out, and what will remain inside is just n minus 1. Okay, and n minus 1 is 5 halves, so what will remain here is just 5 halves. Okay, so from here, no, so this is just equivalent to this, to this, to this. So we are just rewriting it so that we can solve for this. So our goal actually here is that what will remain here inside the gamma function, okay, is 1/2. That's our goal for this. Okay, so we will continue what we are doing here. Okay, so we are going to continue doing this. Okay, this second line. Okay, so we will rewrite gamma of 5 halves, which is gamma of n. We will rewrite it as gamma of n minus 1 plus 1. So in this case, our n here is 5 halves. So n minus 1, that will be 3 halves. So we just rewrite it, ha? So 3 halves plus 1. So from here, okay, so we will apply this. Okay, so our n minus 1 here is 3 halves. Okay, so we will factor out that n minus 1, which is 3 halves. Okay, so we will apply this. Okay, so that will become 3 halves, gamma of n minus 1, wherein n minus 1 is 3 halves. Okay, so again, this is now already 3 halves. So we will have to continue, we have to continue further until it becomes, it becomes 1 half. So from here, again, we will apply this. Okay, so this will, these 3 halves will serve now as your n. Okay, so if we simplify this, okay, so we simplified this. So this is 35 over 4. And then we simplified this. This will become 105 over 8. So here, we will apply this. So we will apply n minus 1. So 3 halves minus 1 is 1 half. So this will become 1 half plus 1. So this is just equivalent to this. Okay, so again, from here, we are going to apply this. Okay, so n minus 1 here is 1 half. So we will factor out 1 half, and what will remain inside the gamma function is n minus 1, which is 1 half. Okay, so we can rewrite it here like this. So this will become 105 over 8. Now we simplified this 35 over 4 times 3 halves. Okay, and then we factor out 1 half. Okay, and then gamma of 1 half. Okay, so from here, we can now stop here because this is already gamma of 1 half, and we know that the value of gamma of 1 half is square root of pi. Okay, that's already an established equivalent, right? Okay, so from here, 105 over 8 times 1 half, that is 105 over 16, and gamma of 1 half is just square root of pi. Okay, so from here, this is already the answer. The 7 over 2 factorial is actually equal to 105 over 16 square root of pi. So that will be the answer already. Now, we can actually use shortcut here. There's actually a shortcut here. As you can see here, okay, so the first one that we factor out is 7 halves, and then we factor out 5 halves, and then we factor out here 3 halves, and then we factor out here 1 half. Okay, so we will use that as a shortcut, that instead of showing all of this solution, okay, so we can just write that 7 over 2 factorial is just equal to first one, 7 halves, times 7 halves minus 1, which is 5 halves, times 5 halves minus 1, which is 3 halves, minus 1. So that will be 1 half, okay, times 1 half, and then times until until it reach 1 half here, and then times square root of pi. Okay, so that is the shortcut for this. So let's say we are solving 9 halves factorial. So 9 halves factorial, that will just be 9 halves times 7 halves times 5 halves times 3 halves times 1 half times square root of pi. So that will be the shortcut for this, okay? So as you can see here, this will just give you the same answer. Okay, so let's proceed now to our second example. So this is negative 1 half factorial. So negative 1 half factorial, actually we already know its its value. That is actually square root of pi, right? But here we're just going to show it here, no? Okay, so using our formula here, so this is our formula for we can rewrite it negative 1 half factorial. We can rewrite it as gamma of negative 1 half plus 1. So we just applied this. So here, actually, if we perform negative 1 half plus 1, negative 1 half plus 1 is actually 1 half. Okay, so if we simplify that here, no, so that will become gamma of 1 half. So gamma of 1 half is actually square root of pi. Okay, so we already know that the value, okay, if it's gamma of 1 half. So for negative 1 half factorial, that is actually equal to square root of pi. Okay, so that will be the answer already for this. Now, for number 3, okay, for number 3, this is negative 3 halves factorial. Okay, so for negative 3 halves factorial, this is negative non-integer with denominator 2. Okay, so we will apply this. Okay, so applying this, now we rewrite it this way. So this will become negative 3 halves factorial is equal to gamma of negative 3 halves plus 1 half. Okay, so if we are going to if you are going to simplify this, negative 3 halves plus 1 is actually negative 1 half. Okay, so this will become gamma of negative 1 half. So from here, okay, from here we are going to apply now this. We are going to apply this. So if we are going to apply this, what we're going to do here is add 1 here. Negative 1 half plus 1. Okay, we will add here. So since we added 1 here, no, so our rule is that we have to multiply this, no? We have to multiply this by the reciprocal of negative n plus 1. So in this case, our negative n plus 1 here is negative 1 half. Right? Our negative n plus 1 here is negative 1 half. Okay, so this will be the negative n plus 1 here. Okay, so we will multiply this gamma function, okay, by the reciprocal of negative 1 half. So the reciprocal of negative 1 half is actually negative 2. So that is negative 2. Okay, so from here, okay, we can simplify negative 1 half plus 1 as 1 half, right? So we can say that this is gamma of 1 half times negative 2. And we know that the gamma of 1 half is actually negative 2 square root of, the gamma of 1 half is square root of pi. So this will become negative 2 times square root of pi. So this is actually the answer already for this. That negative 3 halves factorial, that is actually equal to negative 2 times square root of pi. So let's proceed now to number 4. For number 4, this is negative 5 halves factorial. So this is a negative non-integer with denominator 2. Okay, so we will rewrite this as we use this, okay? So this will become gamma of negative 5 halves plus 1. Okay, so for this, we are going to simplify this. Negative 5 halves plus 1 is actually negative 3 halves. Okay, so after we simplified it this way, so we are going to apply this now. Okay, so we will rewrite negative 3 halves. Okay, we will add 1 here. Also, this will become negative 3 halves plus 1. So our negative n plus 1 here is negative 3 halves, okay? So the rule here is that if we add 1 here, okay, so in order for this function to not change, okay, so we have to multiply this gamma function by the reciprocal of negative n plus 1. Our negative n plus 1 here again is negative 3 halves. So the reciprocal of negative 3 halves is negative 2/3. So we will multiply this by negative 2/3. Okay, so simplifying this, so negative 3 halves plus 1, that is actually negative 1 half. Okay, so from here, okay, we have to continue on, okay, until this gamma of negative 1 half, okay, until it becomes positive 1 half. Okay, so that's our goal here. Okay, so we will apply this further. Okay, so applying this further, we will add 1 here. Negative 1 half, we will add here 1. So since we added 1, we have to multiply this function by the reciprocal of negative n plus 1. So in this case, our new negative n plus 1 here is negative 1 half. So we will multiply this gamma function by the reciprocal of negative 1 half, which is negative 2. So we multiply it by negative 2. So we can simplify this. So simplifying this, negative 2/3 times negative 2, that will become positive 4/3. And then simplifying this as well, negative 1 half plus 1, that is actually 1 half. Okay, so from here, this is already gamma of 1 half. We have value already for gamma of 1 half, which is square root of pi. So we just substitute square root of pi here. So this will become 4/3 square root of pi. So this is actually the answer already for negative 5 halves factorial. So we can actually solve this using a shortcut. So we will use this shortcut. We can use this shortcut. So for negative 5 halves factorial, this will just be equal actually to the what do you call this? What you're going to do here is, let's say 5 halves, negative 5 halves. Okay, you subtract or you add 1. You add 1. So that is negative 3 halves, right? So you just get its reciprocal. Okay, and that is negative 2/3. Okay, and then for negative 2/3, okay, negative 3 halves rather, negative 3 halves, we add again 1 for that. So that will be negative 3 halves plus 1. So that will be negative 1 half. So we multiply that. Okay, or we get that the reciprocal of that. So the reciprocal of negative 1 half is negative 2. So we just multiply it here. Okay, so if this is already, if this is already negative 2 here, okay, if this is already negative 2 here, meaning to say we already reach, reached what we need here. So, we will just multiply that by square root of pi. Okay, and that will now become the answer. And that is 4/3 square root of pi. Okay, so that's our rule for this. Let's say for negative 7 halves factorial. For negative 7 halves factorial, what you're going to do for shortcut, no, you just add 1 in 7 negative 7 halves. So negative 7 halves, okay, plus 1, that is negative 5 halves. Okay, so you get the reciprocal of that. So the reciprocal of that is negative, what's the reciprocal of that? Negative um, 2 over 5, right? And then negative 5 halves plus 1, so that will be negative 3 halves. You get its reciprocal, so that is negative 2/3, right? And then after that, no, negative 3 halves plus 1, so that will be negative 1 half. So you get its reciprocal, that is negative 2. So you multiplied those three, negative 2, 2/5 times negative 2/3 times negative 2. So if it's already in negative 2, no, so we just multiply square root of pi. So that will already be the answer for that. Okay, so for negative 7 halves factorial, okay, so that is just um, okay, negative 2 over 5. That is just actually negative 8 over 15, okay, times square root of pi. So that is the answer for negative 7 halves factorial. So that's the answer for this now. We will now proceed to the Laplace transform of non-integer powers of t. So the non-integer powers of t that we are talking about here, specifically, those are just functions with denominator 2. Okay, so that is just applicable for that. Okay, so we will now solve examples here. So find the Laplace transform of number 1. So number 1 here, the given f of t is t raised to negative 5 halves. Okay, so if you are going to apply the Laplace transform of t raised to n, so as we can see here, okay, so the Laplace transform of this will be negative 5 halves, that is n factorial over s raised to n plus 1. So if we apply that here, so our n here is negative 5 halves, so this will become negative 5 halves factorial over s raised to negative 5 halves plus 1. So the problem here is that if we don't know, okay, how to solve this, okay, that will be a problem. Okay, so since we already talked about how to solve for this type of for this type of factorial, so this is negative 5 halves factorial. We already talked about that. So we know that negative 5 halves factorial, okay, if we use our shortcut for that, no, so you can do that. We can use the shortcut for this. So for negative non-integer, okay, so we can use the shortcut that we just negative 5 halves, okay, we add 1, so that will be negative 3 halves, and its reciprocal is negative 2/3. Okay, and then negative 3 halves plus 1 again, so that will be negative 1 half, okay, and its reciprocal is negative 2. So we just multiplied negative 2/3 and negative 2. Okay, and we multiply square root of pi. So that will already be the answer no for negative 5 halves factorial. So we will simplify that. No? So also s raised to negative 5 halves plus 1, that is s raised to negative 3 halves. So simplifying this, so this will become 4/3 square root of pi, okay, over s raised to negative 3 halves. So this, simplifying this further, no, so since this is s raised to negative 3 halves, so we can rewrite it, no, we can put here in the numerator, no, since this is negative. So if we put here in the numerator, this will become s raised to positive 3 halves, right? Since this is negative here. Okay, so this will now be the answer for this. That the Laplace transform of t raised to negative 5 halves is 4/3 square root of pi s raised to 3 halves. Okay, so this will be the answer for number 1. Now for number 2, the given f of t here is t raised to 5 halves times e raised to 5t. Okay, so for this, we can actually apply first shifting rule for this, or first shifting theorem for this. Okay, because we have here e raised to 5t. Right? So we cannot apply dito ha? We cannot apply s differentiation here. Because for s differentiation, we need that the exponent of t there is a whole number, an integer, because that will that will, if we use s differentiation, that exponent n will determine how many times you are going to differentiate, right, the Laplace transform of the function uh, that is combined with t raised to n, right? So of course, we cannot use that here, since this is 5 halves. So there's no 5 halves times, okay, that you're going to differentiate. There's no such thing as that. Okay, so here we are going to use first shifting rule or theorem instead. So we are going to use this since we have here e raised to 8t, okay, or 5t. Okay, so from here, no, using first shifting theorem, no, so we are just going to solve for the Laplace transform of the function, okay, that is combined with e raised to 8t, which is e raised to 5t, which is t raised to 5 halves. So we just solve for its Laplace transform, and after solving for its Laplace transform, we are just going to replace all the variables s, okay? We substitute s minus 5 to that. Okay, so this is actually s minus a, and our a here is 5. So s minus 5. Okay, so solving for the Laplace transform of t raised to 5 halves. So that will just be n factorial over s raised to n plus 1. So our n here is 5 halves. So that will be 5 halves factorial over s raised to 5 halves plus 1. Okay, and we will substitute or replace all variables s with s minus 5. Okay, so simplifying this, as we know, 5 halves factorial, if we use our shortcut for that, that is just 5 halves times 3 halves times 1 half times square root of pi. Okay, over, okay, so we simplify the denominator here, and we know that 5 halves plus 1, that is 7 halves. Okay, so we will substitute, or we will replace variable s with s minus 5. That's why it became s minus 5 raised to 7 halves here. Okay, so simplifying this further, so this will become 15 times, so this will actually become 15 over 8. Okay, 15 over 8 square root of pi. So we can just bring down our 8 here. So this will become 15 square root of pi over 8 times s minus 5 raised to 7 halves. So this will now be the answer for this. Okay, so we will proceed now to Laplace transform of integrals. So if f of s is equal to the Laplace transform of the given f of t, then the Laplace transform of this, so this is integral of f of t dt from 0 to t. So that will be equal to f of s over s. Okay, so for this, okay, what we're going to do here is that if our given f of t, okay, so if this is the given f of t, integral of any function of t dt from 0 to t, if we get its Laplace transform, that will just be equivalent to f of s. Okay, that will just be equivalent to f of s over s. So f of s here is the Laplace transform of this function here. Okay, so our rule here is that for us to apply this, okay, the given f of t, okay, should be integral of function of t dt from 0 to t. Okay, if this is not the given, we cannot apply this. Okay, so this is any function of t ha, this f of t. So here, okay, we can directly use this, no, that this will just be equivalent to f of s, wherein f of s here is the Laplace transform of this f of t here. This f of t, this function of t. Okay, and we will just divide that by s. Okay? So we will apply the Laplace transform of integrals here. Okay, so for number 1, if f of t is equal to integral of cosine 2t dt from 0 to t, find the Laplace transform. So again, the given f of t is this, integral of cosine 2t dt from 0 to t. So that's why it's called that's why it's called Laplace transform of integral, because our given here is an integral. Okay, the given f of t is an integral. So for this, we can apply our formula here that f of s, the Laplace transform of this, will just be equal to the Laplace transform of this function of t here. So this function of t here is cosine 2t, and we will just divide that by s. So as simple as that. Okay, since our given, it satisfies the condition for us to be able to use this formula. Okay, so for this, no, we know already that the cosine or the Laplace transform of cosine 2t from the table, that is just s over s squared plus 4, or s squared plus w squared, wherein our w here is 2, which is 2 squared, which is equal to 4. Okay, so for this, no, we can simplify this. Okay, so we can just cancel out s here, no? So this will become 1 over s squared plus 4. So for this given f of t, okay, the answer for this is actually 1 over s squared plus 4. So that will be the answer already. Now, for number 2, our given f of t here is equal to integral of t times e raised to negative 2t dt from 0 to t. So we are going to solve for its Laplace transform. So as you can see here, we can also apply Laplace transform of integral here, since this is integral and the limits here is from 0 to t. Okay, so applying the formula here, no? So the Laplace transform for this will just be the Laplace transform of the function here, okay, which is t times e raised to negative 2t over s. Okay, so we will solve for the Laplace transform of t times e raised to negative 2t. So for this, to solve for its Laplace transform, we can either use S differentiation or first shifting theorem. So it depends on you what you want to use. But in this case, we are going to use first shifting theorem. So for using first shifting theorem, okay, we are just going to solve for the Laplace transform of t and just replace the variables s by with s plus 2 or s minus a, wherein our a here is negative 2. So s minus negative 2 is s plus 2. Okay, so solving this, the Laplace transform of t from the table, that is just 1 over s squared. So we will just substitute this variable s, okay, with s plus 2. So substituting that, so that this will become s plus 2 squared. So simplifying this, so this will become 1 over s times s plus 2 squared. So this will now be the answer for this. So that concludes our discussion. I hope that you learn, and I hope that you attain the learning outcomes for this topic. So see to it that you answer the course material assessment task for this lesson, okay? And you will submit that on our next meeting. Okay, so see you soon, class. Keep safe and God bless you. Bye-bye.